Quadrilaterals, section 6. In this section, it's essentially all proofs. So we're taking all of the properties and definitions we've learned in the chapter thus far, and we're applying it to prove different figures to be different quadrilaterals. So all of this section is simply examples. So I encourage you to try doing one of the examples on your own and then watch me do it on the video. So, starting with example number 1, we always start with what we know. So I know BCDA is a rhombus. So that's to say that this figure right here, BCDA, that's a rhombus. So I initially think that all of these sides are the same length, as well as the opposite sides are parallel. Now I know some other things about diagonals and things with a rhombus, but I don't think I'm going to be using that so far. So I start by labeling what I know, and then I also know that BA, so this, equals CE. Okay? So it asks me to prove that CDE, angle CDE equals angle E. So once these proofs start to get a little more complicated, we're going to want to start thinking backwards. So start with what we know and then see what we need to prove. So what I want to prove is that angle CDE is equal to angle E. I'm going to put it in green because I don't know if that's true yet, but that's what I'm working towards. And so I'm going to start with my 2-column proof. We have our statements on the left and our reasons on the right. And I always start with my given, so I know that BCDA is a rhombus. I also know that BA equals CE, and that is given. Okay. Next step. Well, lots of times the second step can simply be you go right off of what you're given. So when I said I was given a rhombus, I initially did all of those markings, saying all those sides were the same and all those sides are parallel. But when I'm looking at it, I'm seeing, since I label all those sides as being congruent, I bet I'm going to use that to show that I have an isosceles triangle over there on the right, because I can kind of see I have that blue line and I have that red line. If I know that those are equal, which I do, I can show that those opposite angles are equal. So I initially see that isosceles triangle on the right, and I think that's kind of where I'm going. So the second step is it's usually stating something a little more obvious. So it's saying BA, so I'm essentially just saying all those sides are the same length of that rhombus. So BA is equal to BC, which is equal to CD, which is also equal to DA. And the reason I can write for that is just the definition of a rhombus. Well, step number 3, well, I see initially that I have BA is equal to something in the given, and BA is also equal to all those other things. So I think I could use substitution to say that what I ultimately want to say is that CD is equal to CE. So because I know that BA is equal to CE, I can kind of plug that in. It's almost like I'm plugging it in here, because I know that BA is CE, and I can plug CE back in for BA down here, and then I know that CE will equal CD. So I just use substitution for that. And then I'm seeing just one more step where I can say, since I know that now that these two sides are equal, I can say that those angles are equal. So I can say angle CDE is equal to angle E. And I know that because of the isosceles triangle theorem. Because the isosceles triangle theorem says that if this is the same as this, then these two angles, those opposite angles, are also going to be equal. Great, now moving on to example number 2. This one is more of a fill in the blank type of example, but we still need to kind of think about it in the same way. So, what am I given? Angle 3 is supplementary to angle 2. So that's to say that this angle plus this angle is going to equal 180 degrees. And I also know angle B is equal to angle 3. Okay, so I'm going to put a red line there too. So I know, so I'm going to see later, I bet I'm going to use maybe that something to do with parallel lines, because I see now I want to prove that ABCD is a parallelogram. So I'm going to put it in green. What I ultimately want to prove is that this line is parallel to this line, and this line is parallel to this one. I don't know that yet, but that is what I'm trying to prove. So we got to think backwards and think, how could I eventually show that those two pairs of lines are parallel? Well, I start initially with my given. It looks like we forgot something in our given. We also need to say that angle B equals angle 3. That is also given. It's a little messy, but angle B equals angle 3. It's in our given. And so the next step, you could go a lot of different ways with this, and it looks like in this proof they said alternate interior angles equal, therefore we have parallel lines. So that's to say, we're saying some two lines are parallel, and it looks like alternate interior. I see that 3 and B are alternate interior, so that would mean, since that this line is parallel to this one, because 3 and B are alternate interior that way. So I could say that AD is parallel to BC. Next step is the definition of supplementary. So in the given, we were given that angle 3 and angle 2 are supplementary. So I think I'm just going to, the definition of supplementary would just be saying that, the sum of those angles is 180. So that one's a little more obvious. You might just assume that. And I also see that angle 3 and angle 4 equal 180. And that's those angles right in here. So it says angle 3 and angle 3 and angle 4. And I know that's the linear pair theorem, which we use a lot. If we ever see a line, we know that those angles are going to add up to 180 degrees. So we use a linear pair theorem. And so I see in the previous two steps, we have angle 3 and angle 2 equal 180, and angle 3 and angle 4 equal 180. So using substitution, since they're both equal to 180, it's like we can set them equal to each other to say that angle 3 plus angle 2 equals angle 3 plus angle 4. So it's almost like we said this is equal to 180, so we stuck it in down here. Next, we need to do some sort of a subtraction. And I see that if I subtract angle 3 from both sides, I'll be left with angle 2 equals angle 4, which I bet will give me something to prove something parallel, which I see that it does. So if I use blue, so I already know angle 2 is down here, and then angle 4 is up here. And if those are equal, then I know that these two lines are parallel. And I know that because angle 2 and angle 4 are corresponding. So corresponding angles equal mean that lines are parallel. So I'm doing that all in the same step. I just ran out of room. And then, therefore, the last step, I say that ABCD is a parallelogram. And I know that because both sides, or let's see, I should really say both pairs of opposite sides are parallel, which tells us that it's a parallelogram. And that's used from the previous section. I ran out of room for parallelogram there, but you know what I'm saying. And so we use the rules for proving parallelograms and rectangles and things like that from the previous section to prove that this is in fact a parallelogram. So look over all those steps and how that logic flowed, what we had to write, what we didn't have to write, and see if you could do it yourself.